And good evening, everybody. Let's get started. So let's start with announcements. Homework 7 is due this Wednesday, 11/11. So take a look at that on Canvas. There's also some op-amp practice problems out there. You'll see, there's the exam review problems, but there are also practice problems linked to the to the Canvas page. And those are meant not just for exam review, but if you're having, if you want some extra practice or see how I solve problems, take a look at those practice problems on op-amps, and I think that'll help with homework. So I am unable to add everybody automatically to the Slack channels now. For some reason, something changed on Slack. So there is the next homework Slack channel. There's the next lab Slack channel, but I think you're going to have to search for that channel and add it to your account yourself. So take a look at that out there. So my office hours will be right after class. Come join if you want to ask any questions or just listen to other people's questions and my answers or their answers. And the TA's office hours are posted on Canvas. And as always, ask questions via unmuting or chatting. And otherwise, please stay muted to keep the background noise low. So I have this Google search that I did. So we're going to talk about hexadecimal today, and I'll give you a little background on hexadecimal. But if this is an interesting article, so go Google hexadecimal, the Martian, and it's about the only time you'll see hexadecimal enter the Business Insider or Hollywood. So I wanted to put that up there. Okay. So let's move over to the whiteboard. And what I want to do is I want to continue our discussion of number systems. So last time we talked about number systems. Stand by, let me try to get my chat up here. It always disappears on me when I change modes here. Okay. So we talked about binary number systems, and I talked about how a binary is a base 2 system, and you can represent a number in base 2 with 2 symbols, 0 and 1, just like in decimal, base 10. You can represent numbers with symbols 0 through 9, right? There's 10 symbols there. And then the position with respect to the radix, remember the radix is the dot, the decimal point, that separates the integer number from the fractional part of the number. And so if you count the number of positions away from the radix, we talked about how that is the exponent of the base when you're interpreting a number. So let's jump into hexadecimal numbers. Not only is it used by people stranded on Mars, it's also used by mainly computer programmers who want to represent binary numbers in a very compact form. And so what I like to do is just start counting, right? So let's do a table of decimal numbers. Right, so that's going to be a decimal number, and then its equivalent hex value. And so if you start counting in decimal, let's just start with 0, right? 0 is hex 0. 1 is hex 1. And so we're going to keep counting up in decimal until we, well, run out of symbols to fill that digit. Right? So decimal 2 is hex 2. And so I'm going to say ... keep counting. And then I get to 9 in decimal, which is 9 in hexadecimal. And I might put some blue lines here to kind of, there's nothing special about where these blue lines are. I just want to keep my table straight. So in decimal, when we run out of symbols in our digit, we're going to return that digit back to 0. And then we're going to increment the next digit to the left. Okay, so we go from 9 to 10. In hexadecimal, you don't have 10 digits, you actually have, or 10 symbols for a digit, you have 16. And so the next symbol that goes in this first digit is A. Okay, and then I can keep counting. 11 is hex B. 12 is hex C. 13 decimal is hex D. Okay, let me draw some more of my blue lines here to keep my rows straight. 14 is hex E, and 15 is hex F. Okay, so this is 16 symbols in that one digit's place, 0 through 9, and then A through F. So I added 6 digits onto the 9, 0 through 9, which gives me 16 digits. Okay, well, so then decimal 16. Well, we do the same thing with hex. When we run out of symbols for that digit, we reset it back to 0, and we increment the next digit to the left. So decimal 16 is hex 10, and then 17 is hex 11, and so on. Okay, and so you can do this. You can count in hexadecimal. It's really not all that interesting if you just count with this table. Just use this table for the sake of counting. But what's good about hexadecimal is because you have 16 symbols, you can represent 4 bits of information, right? 4 binary digits of information with just one symbol. And so let me show you what I mean by that. So if I have some number, let's just specify a binary number, 1, 1, 0, 1, 0, 1, 1, 1, right? So that's a binary number. Now, if you don't see any radix, just like a decimal number, assume the radix is on the right. So I could put the radix over there, but I probably should put down a subscript that says this is binary. So that subscript 2 means that this number is binary. Okay, there's a really neat technique in order to convert binary numbers to hexadecimal, and it goes like this. You start at the radix, and you can go to the left or the right. Let's go to the left, and you have a number of bits over here, and you divide that number of bits up into groups of 4. Right, so there's a chunk of 4 bits. There's a word of 4 bits. There's another word, and what you do is you convert each one of these groups of 4 bits into their respective hex digit. Okay, so first let's convert to decimal. So this binary number, if you remember, this first digit to the left of the radix, that's 2 to the 0, and the next one is 2 to the 1, 2 squared, 2 to the third. So really, this is let's see, this 1 on the right here represents a decimal 1. The next one represents a decimal 2. The next one represents a decimal 4, and then we have 0 times 2 to the third, which would be an 8. Okay, so that converts to a decimal 7. And you could come over to this table here, and you can see, well, somewhere in here, that equates to a decimal, or a hexadecimal 7. So it's also 7 base 16. That's the same digit. Okay, then you move over to the next group of 4. And so this word, this 4-bit word, you pretend like it's isolated. You pretend like it's not in this position relative to the with respect to this radix. In fact, you pretend the radix is on the right side of this 4-bit word right here, and you convert it on its own. So this would be, let's see, this is a 1 plus, this is 1, 2, 4, a 4, right? That's 2 squared, and this is 2 to the third, that's 8. Right? So that's a 13 base 10. And then you convert that 13 to hex. So that, let's see, that hex number in 13 is going to be a D, delta, base 16. And then you concatenate these numbers together. What I mean by that is D7 base 16. Right. So this binary number converted to hex is D7, a 2-digit number. So you can represent an 8-bit word with 2 digits, with 2 symbols in hexadecimal. And it's just a convenient way to express decimal. And the reason I can just concatenate these two together is because what I'm really doing is every time in binary I slide over one digit, I'm multiplying by 2. It's kind of like when you slide to the left one digit in decimal, you're multiplying by 10. In binary, you're multiplying by 2, and in hexadecimal, you're multiplying by 16. And it happens to be that if you shift these 4 bits from the real radix, right, 4 bits over to the left, you're actually multiplying this number by 16, which is why you can, well, just concatenate these digits together, because it's really 7 times 16 to the power of 0 plus D times 16 to the power of 1. Okay, so that's why I said multiply by 16. You shift 4 bits to the left or 1 digit to the left in hexadecimal. But really the takeaway is it's pretty easy to convert binary numbers to hexadecimal. So there's a question, what if the bit word is not divisible by 4? Well, it turns out that if you have 4 bits, if it's not divisible by 4, I'll get to that. So if you have like maybe a 1 over here, I'll get to that in a minute. Okay, so let me show you that. The reason I want to get to that next is because I wanted to show you a more complicated number that actually has values to the right of the radix.
Professor?
Yes.
I was just wondering, like beyond that table, like beyond the numbers shown in that table, like how do you keep counting with the hex? Like do you return to the A, B, C symbols?
Like, if I got up to, let's say, 1 F, right, dot, 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 1, I go, 1 through 9, A, B, C, D, E, F, then the next number would be 20.
Oh, okay, I see.
Okay?
All right, thank you.
Yeah, it's the same pattern as in decimal. When you run out of a symbol, you increment the value to the left.
Okay.
And when you get up to something like, dot, 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 oh, you can't see that there. If you got up to a number like 1, let's just make up a number, 3, F, F, right? If you increment the F, right, it's going to increment to 0. You're going to carry the 1, right? And then this is going to increment, right? And you're going to carry the 1, and this is going to be 4. So 3FF plus 1 would be 400.
Okay.
Okay.
Okay, thank you.
Sure, yeah. But you know what? I don't really use this table. I'll tell you. I use 0 through F on the hex side because this is how I convert between binary and hex, and also between decimal and hex. When I don't have a hex converter around on my calculator or the web, what I would do is I would first, if I had to convert the number 267 to, base 10 to hex, I would first convert that to binary because I know how to do that. And then once I have the number in binary, I can convert each 4-bit word over to a hex digit. So that's how I would do it. Okay. I want to address that question that I had, and let me know if I don't answer it, but let's do this number. So let's see, 1101 is going to be a longer number. 1101 011 00 .011. Let's do that. Okay. And this is so there's the radix right there, and this is a base 2 number. Well, let's follow the same procedure. I'm going to start at the radix. And again, you can go left or right, but I'm going to go to the left here first. I'm going to split this, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is a 12-bit word. I'm going to split it up into groups of 4 bits, right, starting at the radix. And then I'm left over with this 1 over here, right? Okay, so what I'm going to do, remember, this doesn't change the value if I add leading zeros. I can do that to a decimal number. You don't change the number. So I'm going to convert that value, right? And so let's see. So this is, let's see, this is 1, 2, 4, 8. This is 4 plus 8, which is 12, base 10, right? 2 to the 0, 2 to the 1, 2 squared, 2 to the third. So that's 8 plus 4, 12. And 12 is a C as in Charlie. It's a C base 16, right? Now I go to the next 4-bit word. This is 2 to the power of 1 plus 2 to the power of 3, which is 10. So 1, 2, 4, 8. 2 plus 8 is 10, base 10. And that's an A, alpha, base 16. And finally over here I have a 1, right, in decimal. And so that's a 1 in hex. Okay, now we can go to the right side of the radix. And so I only have 3 bits in this word, so I can add a trailing 0. I'll add that 0 there. So I'll convert that, right? That doesn't change the number at all. 2.5 is the same as 2.50 in decimal. Okay, and then I convert this again as it's a standalone value with its own radix over here on the right side of that 4-bit word. And so this would be, let's see, 2 to the power of 0, 2 to the power of 1, 2 squared. Right? So it's 4 plus 2 to get a value of 6 base 10 and also base 16. Let me just write that. 6 base 10, 6 base 16. And then you just write all these values together. 1 A C dot 6 base 16. So this originally 12-bit word can be converted into hex, and that 12-bit word can be represented with only 4 characters. And so you'll see this a lot in computer programming, especially when you're dealing with registers or setting flags, like bits in words that do something. They may turn a port on or turn a port off. We'll talk about that later, but that's how you do it. And the reason it works, again, is because, right, C is really C times 16 to the power of 0. A is A times 16 to the power of 1, right, where A is 10. So let's see, can you go over how you got the number after the decimal place? Sure. And in fact, I'll do another one because that's symmetric. It's actually not a good example, but let me erase that. So this digit represents 2 to the power of 0. This represents 2 to the power of 1. This represents 2 squared, and this is 2 to the power. That's a 3. 2 to the power of 3 right there. Okay. So when there's a 1 in the digits place, I include that value. So this is 2 squared plus 2 to the power of 1, which is 4 plus 2 equals 6 base 10. That's a 10, which is equal to also 6 base 16. Okay. And so if I had another number, let's see. What if there were an 8 after the decimal? What if there were, 8 after the decimal, like 8 bits, eight places? You would just keep going. So if I, for example, let me just write that in here. If I had 1, 1, 0, 1 right here, I just did that one. Let's do 1, 1, 1, 0, something like that. This number, right? Pretend I just appended those bits on. This number would be 8 plus 4 plus 2, right? So that'd be a 14 base 10, which is an echo, E, base 16. So now this would become an E, base 16, right?
Professor Newhall?
Yes.
In the past, I've learned that past the radix to the right, you're going into negative powers.
Mm-hmm. Oh, I'm sorry. Yeah. That's right. That's exactly right. Just like we talked about in binary. Go ahead with your question.
Yeah, I was just curious why in this case we're not.
Well, yeah, because we're not, because we're treating each one of these words as independent from the rest. Okay, when we did a value like 10.1 base 2, right, in binary, we said this was equal to, let's see, 2 plus, after the radix, that would be 1/2, right? So that would be equal to 2.5, right? This is 2 to the negative 1 here. And that would be 2.5 base 10. Okay, so so here, when you do this conversion technique, you're actually converting 4 bits at a time. And the reason I can write this as a 6 right here down at the bottom, right? The reason I can write this as a 6 is because really this is 6 times 16 to the negative 1. Okay, because remember, each one of these positions is the base. You multiply the value times the base to the power of the position. So this would be 6 times 16 to the negative 1 right here. That would equal 6 times 16 to the negative 1. Oh, I just lost my video. Start that up again. You would find out that that's equal to 0.0110 base 2, right? That's exactly what this is. So this 16 to the negative 1 here accounts for the fact that I'm really putting the radix here when I convert this one word, right? So
yeah, just because we're converting it into hex.
Yeah.
Okay, cool. That makes sense.
Yep.
Thank you.
Sure. Okay. So be sure, even when you go to the right side of the radix, when you're converting a value, right? Let me get rid of that one right there. Keep the same order of powers, of positions in your words. So even though this is to the right side of the radix here, this is 2 to the 0 position. This is 2 to the power of 1. This is 2 squared. This is 2 cubed. Okay. All right. So that's how to convert hexadecimal and decimal back and forth. And again, if you're using computers or if you're stuck on Mars, read that article. You'll get it. And it is really convenient. Like if I have all of these bits that I have to represent, instead of writing all of those bits down, I can just use these 5 digits here. And once you start working with these values, you just see A is 1010, C is 1100. You just kind of, there's only, there are only 6 here to remember in binary. So sometimes you don't even have to go through this step of converting to decimal. You can just, in your head, go right to the value in hex. Okay, any other questions on hexadecimal? So we've covered why you might want to use digital signaling. And I talked about bits, binary digits, and I talked about combining those binary digits into words. And when you have binary words, then you can represent values in decimal or hexadecimal, and you could actually do things like math using those digits.
I came up with a question real quick.
Sure, yeah.
In one long word in hexadecimal, how do you tell the difference between like 1A and 1 and A?
Oh, let's see.
Or does it matter?
Let me see if let me get your question down here. So you mean like 1A, I have a number.
Mm-hmm.
And or two separate numbers?
Yeah. And
well,
if like they were all in a word together, like does that matter?
Yeah, you know, so typically, so it's kind of like numbers. How do you know this is a decimal number 23 and it's not 2 and a separate 3, right? I guess you just know how many digits you're working with if you're working with numbers. If you have, let's suppose you have like a string of bits, and this happens, right? You'll send binary data over the air or down a wire, right? Something like that. You don't really know, right? If this sequence starts at some time and ends at some time, you don't really know where to draw the line for, let's say these are, you know, I don't know, 4-bit words, or let's call it 8-bit words, right? How do I know where the division happens? It could happen here, it could happen here. Well, I have to tell you, and there's something in digital communications called symbol synchronization. So you would actually have to be given the boundaries, right? For example, you might have to be given that, well, there's a division here. This is where the 8-bit word starts. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, right? Something like that. And then you can convert each one of these 8-bit words because you know the synchronization. Typically in digital communications, sometimes there's a starting flag, which is a certain sequence of bits. And when you see that sequence of bits, you say, ah, that's a special sequence, and I'm going to start my symbol counter right there. Okay, does that kind of answer your question?
Yeah, that does. So then if you were converting from hex to just a regular decimal, like a base 10,
yeah,
you could, like, 1A, converting 1A is the same as converting a 1 and then an A.
Oh, okay. So converting 1A and converting 1 and then an A, right? Those are different problems. So
Yeah.
so this would be, and these are base 16. So this would be 10, right? Base 10. This would be 1 base 10. 1A would actually be 0, 0, 0, 1, 1, 0, 1, 0. And A converts to 1, 0, 1, 0, right? Because it's a 10. And so then I would convert this to, let's see, this is a 2, 1, 2, 4, 8. This is 8, and this is 16. So this number would be 26, if I did that right. So separately, this A has a radix right here. This 1 has a radix right here. This value has a radix, well, right there. So when you convert from hex to decimal, first go to binary. That lost my video again. First go from hex to binary, and then go from binary to decimal. I think that's the easiest way.
Okay.
Okay. So this process of going from here to here was just the reverse of what we did up here. Here I went from binary values, right, to a hex value. Here I'm going backwards. I have a hex value, right? I have 1, or let's start with A. I have A. So A converts to a value of 10, and 10 in binary is 1010, 2 plus 8.
Right. And then 1 is 1, but it's to the power, or times 16 to the power of 1. So
Right.
it's 16. Okay.
Right. So, yeah, another way of writing this is 1 times 16 to the power of 1 plus, I'm going to write this way, A times 16 to the power of 0. And yeah, and A is really, right,
Cool.
10.
Okay. Yeah.
Right. So 10 times 1 plus 16 times 1, so you get 26.
Okay. That was helpful. Thank you.
Sure. So what I want to do is move on to digital logic. So digital logic is a way for you to use electronics to make decisions. You can build circuits that make decisions. We're going to talk about combinatorial logic. And combinatorial logic is this. Let's suppose you're trying to make a circuit that again makes a decision. But let's pretend like we have a decision to make. Let me make up a decision. The decision is whether or not to engage the starter motor of a car, right? Whether or not to start the car. Turn the motor that engages the solenoid and turns the engine and starts the car, turns everything on. There are inputs to that decision. Like the output is turn the starter motor or don't turn the starter motor. That's the output. The input is, well, the key, right? If you have a key, right? Is the key switch engaged? Is the key turned? And so that's one input. But you might have other inputs. Other inputs might be, is the driver's foot on the brake, right? Is the brake pedal down a little bit? So there might be a switch there. So that's another input. You might have an input, is the transmission in park or in neutral, depending upon the transmission. You know, there might be a transmission sensor switch. You might have an input that is the airbag deployed? Maybe if the airbag is deployed, the car's been in an accident and you want to make sure the car does not start. So you can think of other safety features. So all of these inputs are true, false inputs, or yes, no inputs, right? Or 1, 0 inputs. They are binary. We're going to call them Boolean, named after a guy, of course. So Boolean logic has to do with representing states of inputs and outputs with ones and zeros. There we go. Zoom likes to drop me. So you have multiple inputs. The inputs are trues and falses, and then you have one output. It's a true or a false also. True, turn the starter. False, don't turn the starter. Okay. And it's also based, combinatorial logic is also based on the present inputs. And what I mean by that is you don't care if the key was turned 3 minutes ago, or if the brake was pressed 10 seconds ago. You care about the inputs right now. Combinatorial logic acts on present inputs, right? To make a decision.
Basically at the current time, correct?
At the current time, yeah. I like to say, I hate using the word current. I used to use the word current in the past, and someone says, so what about voltage? Well, no, not that kind of current. So yeah, at the present time. Okay, and what combinatorial logic uses are circuit elements called gates. Gates themselves make very fundamental logical decisions. Okay. So what I'm going to show you, I'm going to show you the common logic gates, and we're going to talk about those and what they mean. And then I'm going to show you, well, I have a bunch of inputs. How do I use these logic gates and put them together to make a decision based on what I want the circuit to do? Okay, so we're going to start off with gate definitions. We're going to work with those a little bit. And then I'm going to talk about synthesizing logic circuits. Synthesizing means creating a logic circuit that does what you want it to do. So let's start with gates. Let's talk about the AND gate. So here is the symbol for an AND gate. Draw a little better. Like that. So here I have the inputs on the left. And I have the output on the right, as drawn here. So the AND gate is this symbol that has, kind of this flat part and then the curvy part in the front. And we're going to give Boolean values. By that, I mean logical variables to the inputs and the output. I'm going to call them A, B, and C. Okay. Let's talk about A, B, and C. A, B, and C are logical variables. That means they represent ones or zeros. Now, in a real circuit, there's going to be a voltage here. There's going to be like, in 5-volt logic, nominally, 5 volts would equal a 1, 0 volts would equal a 0, as we talked about last time. But when we work with gates and logic, we're going to set aside what the actual voltage values are. We're going to say we don't care that it's 5-volt logic or 3-volt logic. We're not going to measure voltages here. We're just going to assume that A can either be a 0 or a 1, B can be a 0 or a 1, C can be a 0 or a 1, and there are voltages that represent 0 or 1 in this voltage logic. Okay, so you can describe the AND gate by its truth table. A truth table is a table that lists inputs on the left, generally, and the output on the right, like this. On the left, we list all possible combinations of inputs. A good way to list all possible combinations of binary inputs here is to start at what I would consider, well, either binary 0 or decimal 0, and just count up, right? So that's a 1, that's 2, and that's 3. And once you've filled all of your bits, both of your bits on the left here with ones, you've exhausted the possible combinations of inputs. On the right, you put the output for this gate. And the AND gate answers this question: are both of my inputs true? Right? So every time you see an AND gate and you see what it's doing, you're saying, are both of my inputs true? Okay, so for this first set of inputs, if I have a 0 equal A equals 0, B equals 0, the output is going to be 0. Both of my inputs are not true. If A equals 0, B equals 1, no, both of my outputs are not both of my inputs are not true. If A equals 1, B equals 0, no. Both of my inputs are not true. They're not 1. A equals 1, B equals 1, yes. So the only way you get a 1, a true, out of an AND gate is to have both inputs equal to 1. So this is a way to represent the function of an AND gate, what it does. There's another way, and it's using Boolean expressions. Boolean expressions are equations of variables that are logical variables. The variables represent 0 or 1. That's what a Boolean expression is. So this is actually a Boolean multiply or a logical multiply. So whenever you see C equals A times B written like this, that also means an AND gate, right? So A could be 0 or 1, B can be 0 or 1, and this multiply operation, this logical multiply, implies, it means, it's defined as doing what this table says. Okay. And I think as we get onto other gates, you'll see how this is working. Let's talk about an OR gate. It's one of the other fundamental gates. An OR gate looks like this. So like that. Kind of got this curved, instead of a straight side with the inputs, it's curved back there. And so, and it comes to a point here instead of being round. A, B, C, so inputs A and B, output C. The truth table for an AND gate is this. So I list all possible combinations of inputs, 0, 0, 0, 1, 1, 0, 1, 1. The OR gate asks the question, are either or both of my inputs true? So are either or both of my inputs true? No, yes, yes, yes. So that's how an OR gate is defined. And it's called in a Boolean expression, a logical addition. So C equals A plus B. It's a logical add. Okay, so in this case, 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 1. In this case, 1 plus 1 is 1. So in Boolean expressions, 1 plus 1 is 1. The plus means or. It means what this truth table says. Okay, so let's look at a logical inverter. This is another gate. It looks like that. It's got a triangle, a bubble on the output of the triangle, and it has one input and one output. And its truth table is really easy. It just gives you the opposite of what you put in.
Question.
Yeah.
Are there also NOR and XOR gates?
Yeah, we're going to get to those.
Right.
Yes. Okay, so all possible combinations of inputs is easy here on the left, 0 and 1, and the right is the inversion of the left. So the output is the opposite of the input in the logic sense. The way to write this operation in a Boolean expression is like this. You put a bar over whatever you want to invert. Okay, So that's how you write the logical inversion in an expression. Then there's something called an exclusive OR.
Professor,
Yes.
is there a name for that Boolean expression, like how we had logical multiply and multiple add?
Yeah, you know, you can, I've heard different people say it different ways. They'll say A bar or inverse of A or A inverse or inverted A. And unfortunately, yeah, I have heard many different names for that.
Okay.
So I will generally say inverse of A, or I'll say not, N-O-T, not A. That's another way of saying it.
Okay. Thank you.
Mm-hmm. So the exclusive OR looks like this. It kind of looks like an OR gate. If I can draw an OR gate. And it has this extra fin on the back like that. Okay, so A, B, C, like this. And so its truth table looks like this. So the exclusive OR gate asks the question, is either input true, but not both, right? The OR gate, either or both inputs could be true. Here, is either input true, but not both? No. Either input true, but not both? Yes. Either input true, but not both? Yes. Input true, either input true, but not both? No. Okay, so that's the truth table. You'll see XOR written as XOR, or exclusive OR written as XOR, or called an XOR gate. And you represent XOR like this. C equals A plus, but with a circle around it, B. Okay. This is also called, and this will be relevant next lecture, but a modulo 2 addition. It's called a modulo 2 add, and I'll show you why that is. But if you see modulo, M-O-D-U-L-O 2 add, that's an exclusive OR gate. Okay. Let me erase this and I'll show you 2 remaining gates here. So as someone mentioned, there's something called a Nand gate and a NOR gate. So a NAND gate is an AND gate, it's supposed to be rounder than that, right? Followed by an inverter. And I should have drawn the AND gate first. Let me redraw this. The NAND gate itself is actually this. And it's equivalent to an AND gate followed by an inverter. So you take the truth table of an AND gate and you invert the output. A NOR gate is this. The bubble, whenever you see these bubbles like that means, typically it means invert in the logic sense. This is an OR gate followed by an inverter. And so with these gates, right, the AND gate, the OR gate, logical inverter, exclusive OR, NAND, and NOR, in fact, with 3 of these gates, the AND, the OR, and the inverter, you can make lots of decisions. You can implement what I described with the car starter. You want the airbag not deployed, you want the key turned, you want the transmission in neutral, you know, you want whatever. You can take these gates and implement a larger truth table, and that's what I'm going to show you how to do next time. Okay, so let's wrap it up here. It is 6:10. In closing, don't forget to check out pre-Lab 9 and Lab 9. They are posted for this week. If you want to jump on Slack, remember I'm not able to add you automatically to channels, so do a channel search if you want to find the Lab 9 Slack channel and the homework Slack channel. So thanks for joining class. I hope it's working out well. If anything isn't working out well, please let me know. And I will start office hours in just a minute, or I will see you next time.